worries. Got someone else waltzing in at the moment. Yeah, that's fine. Question 1. Okay. Oh, okay. Um, okay. Yes. Everything's set up online. Start whenever. Okay, well, it's 12 o'clock, so try to get started here. This is the C Programming Basics training class. My name is Todd Evans. I'm staff here at TAC. I'm going to be using some slides that are borrowed from my colleague here, Ritu. She put together a nice set of slides for this. This is going to be from noon to 4, so it's a long time. Hoping to take frequent breaks. Maybe start every session roughly on the hour, see how far we get, and then take a 15-minute break after each one, or 10 minutes, whatever makes sense. At any time, feel free to stop me and ask questions. We're going to go as slow or as fast as people want. People here in the room have priority with how we're going to proceed. This is truly a basic class, so you're not going to become an expert in C after doing this. Learning a programming language, as you might be familiar with, it's a lot like learning a foreign language. And so you need to just become immersed in it, and spend a lot of time in it to become an expert with it, become fluent with it. But hopefully today we can teach you to do things like say your name, my name is, and count to 10. The idea is just to be comfortable with putting together a C program, knowing what the different components are of it, being able to compile it, and being able to run it. And I think we'll be able to achieve that. This is my email address, rtevans@tac.utexas.edu. If you guys have any questions later on, you should feel free to email me. This works. So these are all the topics we're going to cover today. I'm going to start with just writing a basic C program, get your hands dirty right away. We'll compile it and run it, and then we'll move on to understanding errors, which is actually one of the most important components of writing code, because as you'll find out if you stay in working with code for very long, for some reason it's almost impossible to write a program and have it work correctly the first time. I don't know why, but you get really good at understanding errors and identifying what they're telling you and how to fix them. Then we'll move on to like the grammar of C, the comments, the keywords, the identifiers, and variables. And you'll see that there's not a whole lot to the language as far as numbers of total number of different words that describe language, but you can do an awful lot with these. And then we'll move on to things like standard input and output to get you started. Then go on to operators, like mathematical operators, comparison operators. Then move on to control structures, which is things like if-then statements, and nothing terribly complicated, but you'll see the syntax for them. And then we'll move on to describing the basics of how functions work in C. And we should get to arrays and structures. I don't know if we'll get to pointers and working with files. We'll just see how that goes when we get there. So first step, of course, when you're creating a C program is to have some idea of what you want to program. Then you're going to write what we call the source code, which is the code that it's readable by a human. You can look at it and understand it. You do this by using a text editor like Emacs or VI, or some people like to use an integrated development environment. They call it an IDE. Personally, I find those a little bit confusing. I'm definitely not an expert with them, but I'm pretty good with Emacs and VI. So if you have questions about those, definitely let me know. If you have questions about IDEs, I'm sure we can figure it out too. Then you do what's called compiling the source code. So you take this code that's written in a language that you can understand and write and make sense out of, and basically turn it into ones and zeros so that the computer can understand it. It's like a translation between our kind of way of thinking and language to a computer's language. And then you do what they call link the program. So if you have multiple different files that you've compiled, linking it combines them all together. So if you define some functionality in file 1 and some functionality in file 2, then linking them will make both functionality from one available to the other and vice versa. And you'll see some examples of all of this. And then you've got to fix any errors, which, like I said, for some reason they're always there. Run the program and test it. And then more likely than not, you'll find bugs. And bugs are not necessarily, it's not like there's something grammatically wrong with the code. The syntax is fine. The compiler thinks your code's okay. But it's doing something unexpected. It's maybe adding two numbers as opposed to multiplying them. So it's a change in the functionality of the code. So this is going to be our first code here. It's extremely simple. It's identical to the Hello World code that you've probably heard of, at least in the past. And how we're going to do this in this class is cut and paste directly from the slides. We call it CPR, cut, paste, and run. So we'll cut and paste directly from the slides. Oops. And let's see if this works. So you should be able to highlight these lines, open up a text editor, cut the lines out, and plop it into the text editor, save the file, and then we can compile it and run it. But I guess we need to figure out, has anyone here not been able to install the compiler at this point? Yeah. So you can do it different ways. If you have the compiler here on your local machine, if you have like a Mac or whatever, you should be set, or a Linux box. If you have Windows with Cygwin, you should be set up too. And see, if you don't have those, we can just log into our machines here. We have a training account. Jason, do you remember what the training account name is? Yes, yeah, to get the slides themselves. Yeah, I forgot to put that up. Yeah, yes, please go to the website, get the slides. I'm not sure how to do that. Okay. This one. Yeah, I'll be able to show you the URL here in a minute. You can just go directly there. We're expecting this process to take a few minutes to get everyone set up with being able to actually cut and paste into the source code. So we can walk around and help everyone if things are looking tricky. No, you can download it now. Yes, you can just SSH into Stampede. That's great, but you'll need the slides. Great. That's perfect then. Yeah, if you can SSH to Stampede and you know how to do that, you're pretty much set. Okay, so this is the website up here. If you go to here and you just click on the very bottom, the link to download course materials, that'll pull down all of the slides. And then you'll be able to cut and paste directly from those slides. Okay, so you guys, great. Yeah, that's going to be the easiest if you can just SSH to Stampede and you open up. Has anyone here like not used a text editor like Emacs or VI? I can show you how to do that. So, yeah. Okay. So. Oh. Oh, you're logged into Stampede already? Okay, so this will be great. So you should just be able to type Emacs. And I don't know, it should say how to get rid of this somewhere. Oh, let's try. What was it? Test.c. Just test.c. Okay, so it just wants the name of the file. And so you'll be able to cut and paste into that and give it, probably easiest if you open up a file with that name, this first code.c. And then how you save it, hold Control X and Control S. Okay, so it saved it, and then we can just do Control X, Control C. Yeah. Yeah. If you have any problems with this, just let me know. We'll figure it out. Did you have some questions about this? It might. What happens if we just type GCC? Let's see, can we SSH? Yeah, so SSH is just H, and then you have an account on Stampede. Have you ever logged into the TAC user portal? Yes. So do you remember your name for that? Oh, okay. Okay. So yeah, we'll want to reset this password. I don't, you can help him out? Okay, thanks. Are you feeling okay with this so far? Yeah, sure. Yes, Sigwin. Do you have an account on the tab? Do you remember your name? So we'll want to, if you type SSH space, then your username, and then right after that @ yeah, no space, Stampede, STAMPED dot ED, E dot UTexas dot edu. Yeah, and then hit enter and see what happens. Let's try typing GCC. GCC. Hit enter and see what happens. Okay. Jason should be able to help you get that installed. So either we'll get GCC on your machine, or we'll get SSH set up on your machine. Which one? That's not necessarily the easiest thing, but I don't understand why that's not working. Old Sigwin. Oh, this says min. This is min GW, which actually might work. Go in there. Oh, yeah, let's try that. See what happens. Oh, let's go. Type GCC or something like that. Yeah. Let's see. Okay, that's fine. That's good. I think it's just this computer, but that's fine. You know, that'll be just fine. But now I need to find this file. Yeah. So I just don't know how where Windows puts these things, but we can get it figured out. Are you doing okay? Perfect. Awesome. You doing okay? Great, great. And how about you? Is this working out at all? Yep. Great. That's great. That's great. Yeah. Yep. Okay. Slides are not opening. I don't know why.
Did you unzip them?
Doesn't seem to be able to unzip them. Just type Emacs, E-M-A-C-S. Oh, sure. Yeah, you can just type VI then. And VI, let's just say firstcode.c. Yeah. And then if you can cut and paste into that from the slides. You can, yeah, exactly. Yep. Yeah, and then I don't recall how you save in VM. It's like escape colon W or something. There is a cheat. Oh, okay. Great. Okay, that's great. Yeah, so I'll definitely go through that. If you want to right now, though, you can just type GCC space and then the name of that, and then dot slash dot forward slash a dot out. A dot out. Yep. And that'll run it. But I'll go through that in a little bit more detail. Okay. Let me just explain some of this then. Seems like most of the folks here have things set up. And I don't know if anyone's tried to compile yet, but I'll show you how in a minute. So, understanding our first code. First line here has the pound sign, or I guess nowadays the hashtag include, and then angular brackets. Inside those angular brackets, stdio.h. So this first line is what they call a preprocessor directive. So the first thing that the C compiler does is go through the code and look for preprocessor directives and convert them into something else. So in this case, all this means is include whatever is written. This is a file somewhere on the computer. It's somewhere, stdio.h is on the computer somewhere. You can go and look at it. You can open it up, see what's in there. It's just a file, and the include means just take whatever's in that file and put it at the top of this file, this source code, firstcode.c. The angular brackets here, they have a special meaning. They tell the compiler where to look for this file, stdio.h. So it knows, because of that, okay, I have to look here. Here's the file. It grabs it, and then it just slaps whatever's in there up at the top of firstcode.c. stdio.h has things that let you do input-output. It's standard I/O, input-output operations. And anytime you see a file like this, that's exactly what it's doing. It's just taking what's in there and putting it at the top. And there's a whole bunch of different types of files like this. You can define your own, you can build your own, you can download other people's, and add them to your code. And then there's several standard ones that all start with std. And we'll see a few more of those later on. Now this next line here says int main. Main is our first function that we're looking at. Every C code has to have a main. And it can only have one main. It is where the computer jumps into the code, and it's also when that function's done, that's where the computer gets out of the code. In C, the main function always has to have this int in front of it. This int means that's the type of object that the function returns. So if we look at the bottom of main, you see this return 0. So integer or function main returns the integer 0. We know that this is the end of main because we have opening brackets here, an opening bracket, and then we have a closing bracket down here. So in C, how functions are defined, what belongs to that function is defined as everything that's within those brackets. So printf is another function. It appears inside the main function. And all printf does, as we'll see when we compile this and run it, is take this string, introduction to C, and print it out to your screen. Let's see, what else? So strings in C are defined by these double quotes, and that's just going to mean that it's a series of characters, letters, numbers. It's just symbols. They don't have any meaning other than it's symbols. Now this printf, when it appears like this with a semicolon after it, these semicolons are very important in C. That's called a statement. And C knows when a statement's done by looking for these semicolons. So printf is a single statement, then return 0 is another statement. It's pretty much the simplest non-trivial function that you could possibly have. There's only two statements. Printf, which is a function itself, and printf is defined in this header file. So the compiler and the computer know what printf means because it's described in stdio.h. If you didn't have this, it wouldn't have any idea what it meant, and it would just break or that you'd have errors reported and it wouldn't compile properly. The last thing is this, what we call a new line character, /n. And all that does is tell when the C compiler gets to that line, this \n, it'll start a new line. So it's like hitting enter when you're typing. And I think that's, yes. Yes, not every file, every code, every entire application. So you might have, there will only be one file that has main defined in it. You might have other files that make up the same code, and they'll all be combined later on, but none of them will have main. Main is always where it jumps in and jumps back out. It's just like, it's just the way C was written originally. So main just has to have type int. It has to return an integer at the end. Now, how this could be useful, but it's rarely used this way, like conventionally, if it returns 0, then it finished successfully. And so if you called this function from somewhere else, or this code from somewhere else, and you get a 0, you know, okay, that completed correctly. Now, if it returned a -1 or something, which you would just say return -1 if something bad happened, then you would know, okay, that it failed. But all it can do is return an int, and it always has to be defined that way. And that's just how they set it up in the first place. There's nothing deep to it or anything like that. Yeah. Yes, yeah. Yeah, white space doesn't really mean anything in C. No, it's not like Python, that's right. It's all the scope and everything that belongs to functions like are defined by these brackets. Okay, so now we're going to try to compile our first code. It sounds like some of you have done this, but does everyone know how to save their program? Is there anyone that's having trouble saving the source code after they've cut and pasted it? So after you save it, you should have a file that exists named firstcode.c. Okay. So after you've saved it in that file, somewhere on your computer, you want to go into that same location, that same directory, and we're going to start by just typing GCC. GCC is our compiler. It's the GNU C compiler. -O, and this -O is just an option that tells the compiler what to call the final product, the final. You call it an executable or a binary. It's just to give it a name. If you don't have this -O, it'll automatically create a file named a.out, which you can run. It's the same thing, it just doesn't have a very descriptive name. And then you give it your source code, firstcode.c in this case. And basically, like I said, what it's doing at this point is it's translating the stuff that you wrote and that you can understand a little bit into something that's just machine code. It's just ones and zeros after that point. And then we'll run the program. This is how you run it in a Unix type environment, at least from the command line. It's just // and then the name of your executable. And you'll have to repeat this every time you change something in the code and want it to appear in your executable. So every time you change something and save it, you got to change it, save it, compile it, and then you can run it again to see the changes. This makes it different than something like R or MATLAB or Python, where you can just change it and run it. This is a code that or this is a language that you have to compile. It's not. The other types are called a scripting language or interpreted language. This is a language that needs to be compiled. Is anybody having any trouble getting this to run at this point? You'll be able to save it in there and run it from there. Yeah, where are you right now? This is on Stampede. And what is this one, though? Is that on Stampede as well?
Yeah, I think I just did.
Okay. Is it in there? Can you go to there from here? Stan, I don't know enough about this particular setup, but how quickly this gets synced. There might have to be some syncing that happens, and it's not happening quickly enough. Yeah, absolutely. Yeah, Emacs or VI. Give it a name, a file name first. So if you close out of here with Control C, Control X, Control C, or something like that, and type Emacs and then the name of the file that you want it to be, and then it'll skip that weird screen. Yeah, yep. And then you'll have to save it after you cut and paste into here. And there's a cheat sheet in the source materials, but to save it is, the only two things you'll really need to know is to save it and to quit. So Control X, Control S is to save, and Control X, Control C, I think, gets you out.
Yeah.
Cool. Okay. He's good. Anyone else need a hand? We're happy to take whatever time we need. I think we'll get moving a little bit faster once we get into the rhythm of this, but okay. Well, I'll move on to the next couple of things here. I think we have a few slides before we do another hands-on. So there's different types of C compilers out there. The main ones that you'll run into, or at least that I've run into, are the GNU C compiler. And this one's pretty great because it's completely free. It's available on almost, it can run on almost any operating system. It's what like Linux is built on top of, things like that. And then we have the Intel C compiler, ICC. You can see it works exactly the same as GCC. And this one typically costs some kind of money. If you're a student or doing it for some non-commercial purpose, I think you may be able to get a limited license for it. But it has nice things like it's optimized for Intel architectures. Or certain types, it'll optimize a little bit better sometimes than GCC. And it's actually what we use here at TAC because all of our systems currently are Intel chips. But we also have GCC on the systems too, and you're welcome to use that. But like I said, ICC has some nice features, particularly when it comes to optimization. and it works basically the same as GCC. And there's also the Portland group. I forget what the I stands for, but it's also a C compiler, and I've seen this on quite a few supercomputing platforms as well. Not sure if we plan on getting this onto our systems in the future. I've heard talk of it, but I don't know that that's necessarily going to happen. And if you want to subject yourself to a little pain, you can type gcc-help or --help and or man GCC, and you'll just see a huge number of options and documentation on all the different craziness that you can do with this, all the different flags and ways to optimize the code and help guide the compiler. Now, I mean, I don't know what 90% of those things do or mean, and they tend to be sort of for very specific purposes, and we're not going to really worry about more than one or two of those today. So what makes up, yeah. The -o, that is the name that is given to the file that is output from the compiler. So the executable will be named -o, or the binary will be named whatever comes after that -o. It's what you call an argument to GCC. So what makes up the C language? So different keywords, like you just saw the keyword return. Okay, that's a type of keyword, and there's rules to use those keywords. In the case of return, you have a space and then some other object. In this case, it was 0. Pretty simple. It's not necessarily a reason that the keywords are used in the way that they are. It's just they had to do something, and that's what they ended up with. Then you also have standard header files, like we saw where printf comes from, that stdio.h. There's a whole bunch of these standard header files that exist and that come with the C compiler, and it lets you do basic things like print to the screen or manipulate strings, and we'll see some more of that later. Then we also have preprocessor directives, like that #include, which told the compiler to include that code that's in stdio.h at the top of the source code. And you always have to have one and only one function main. Then you use parentheses and braces in order to organize the code, and they help to tell the compiler what belongs to what, who belongs to who, how statements flow. And you'll see plenty of this in a little bit. Then there's simple things like the semicolon, which, again, that defines where a statement ends. And then you have operators like plus, minus, division, mods, and you also have comparison operators, like if this equals that, then do this. And then there's a few other things also that will come into making up the language or the grammar of C. So let's just do a little pop quiz. There's a few blank spaces here. What does anyone remember what goes here? #include, yep, and that's a preprocessor directive. And then what are we missing at the beginning and the end of the main function? Yep, brackets. I guess, what are the curly ones? Curly brackets, and then, yeah, I'll just call them curly brackets. And I'm not even going to bother you with this one. We got a semicolon missing here. You guys are probably familiar with that by now. So now we'll move on to understanding errors. One of the most important things to any computer programmer. Don't worry too much about the classification of these errors. They're all errors, and you don't necessarily need to know the name of them to figure out how to fix them. But let me go through them anyways. There's compile time warnings, which you don't necessarily have to fix, but it's the compiler warning you, like, hey, something might be wrong here. This could break something else at some point later, or maybe it's not going to work the way you think it's going to work. And there's compile time errors. So when you actually type GCC, the compiler goes and give it the name. When you run GCC, the compiler goes through the source code and looks for stuff that it just completely doesn't understand. So if you just totally botched the printf, spelled it the wrong way, or used a $ include instead of a pound include, then we'll say, hey, this is an error. I don't even know what I'm looking at. Link time errors are a little bit trickier. So when you compile a code, a lot of times there's multiple files that make up an application. And when you compile it, the compiler first goes through each file and just does the translation from the source code into the machine code. Goes through each file, and then at the end of that, it links all the files together, and that's what they call linking, into a single application that you can run. And sometimes it won't know if you have a function, you're calling a function in a certain file, say file 1, and it's looking for the name of this function somewhere at link time, and it doesn't find it if you haven't defined it somewhere else, then you'll get a link time error. But it won't know the first time it goes through that that function's missing because it hasn't already looked for it in other files. And then the trickiest maybe are runtime errors like null pointer assignments, or if you've ever heard of seg faults. That's when you try to access or touch a place in memory that you're not supposed to be touching. And then that happens a lot. And it's not particularly informative. Usually it's because you have an array of a certain size, and you think it's a different size. That's a very common one. And then bugs, which, like I mentioned before, unintentional functionality. These tend to be a little more subtle, and it's usually more like you just accidentally used a subtraction instead of an addition sign. So we're going to go through a few programs here and explore what types of errors we can create. So this one's, you're going to want to open up a new Emacs or text editor, or whatever you're using, and cut and paste this into that, and then save it. You guys can probably already guess what's missing here, or what's wrong here, but we'll just see what the compiler tells us. So if you're not done cutting and pasting and saving, that's fine. But the next step will be we're going to compile this file. So this compile line here, it's GCC. It has the option -w all, and that means give a warning for everything. If you think something should be a warning, print out that, hey, I'm warning you, this isn't good. Then we've got our -o to error.o in this case, and error.c. The -c here That's an option that says we're not going to perform the linking step yet. We're not going to look and check to see that everything's linked up. So if you're compiling multiple files that you're going to combine into an application in the end, you would use this argument -c just to compile each one individually. You don't have to worry about the details of that, but there's a lot of times where you'll do this. You can't run error.o. It's not an executable, but it is a binary. It is in terms of ones and zeros. And that's what the -c here does. And then after you do this, you should see, first of all, oh, hey, there's something going on in function main. And then I believe this is on line 4. There's an error. We expected a semicolon before this. So the compiler recognizes that this is a problem. And then you've got a warning, which who knows what that means. Control reaches end of non-void function. It's not particularly informative, but it's just a warning, so let's not worry about it for now. Does anybody need help with this part? Yeah. Yes. Yeah. That's exactly right. Yeah. It's an integer type function. It's main. You can see main is expecting to get an integer, but it never gets to that return keyword to get the integer. So it's getting to the end of this function, and the compiler knows this probably isn't good. You're not returning something when you're supposed to. Can I help anyone with? Is anyone not seeing these errors and warnings? Uh-oh. Okay. Do we have the -w all? Yeah. So yeah, that's it's another thing with errors, and there's not necessarily anything wrong with that. With errors and warnings that are reported, it can vary by version of GCC. It can vary by the operating system that you're on. And so if you don't see exactly this, you just might not be on exactly the same system. You should see the errors, because the compiler needs to know that it's an error, but the warnings, sometimes it'll report different things with different versions. Okay, so on the next slide, we have that source code where we have corrected the error. It said, hey, on line 4, I expected a semicolon. I didn't see one. And so we went back, added that semicolon, and we're hoping we're good. We got rid of the error. Now you get the warning? Yep. Okay. So now we run it again. We compile it exactly the same way as before. And the error is missing, but you still see a warning. Now it's interpreted it as something slightly different. You're declaring a function, but this function's not defined anywhere. Maybe that's okay. It doesn't know yet, but it's thinking that it's not okay. And then when we do the linking step, which is the gcc-o ctraining.exe space error.o, that's where we're linking error.o. In this case, it's just a single file, so it's kind of weird to link it, but you can still do that. In the linking step, then it goes and it looks for the definitions of all the functions that appear in the source code. And it realizes, okay, retrun is not a function defined anywhere. And you should see this error, undefined reference to retrun, and then it'll just exit out. And then on the next slide, we have the corrected code. And we should just be able to compile it and run it like normal. And hopefully we don't see any more of these problems. Oh. Yeah, if you cut and paste this directly, you'll realize that there is still an error in this file. It's a different error than the ones previously. And you'll see that when you try to compile it, it'll give you an error stdio.h. There's no such file or directory that it can find. So when it goes and looks in this #include and tries to find this file stdio.h to expand, it can't. It thinks that it needs to be a space stdio.h space, and that is not. Yeah, that's not something that you would necessarily expect or know. There's no way that you could know that that's so important, but that's just the way that the compiler works. And at least now, when you see that in the future, you will know that that's probably why. Let's see. Okay. I'm going to take a 5-minute break. And we can just make sure that everyone's caught up and comfortable. And so right now is a great time to ask any questions that you have, or if you're having trouble with anything. So -w all that means is report every warning. If you don't have that, the compiler, it kind of like ranks warnings by severity. I don't know exactly how it decides, but if you do -w all, then it'll print every warning that it picks up. Right, yeah, it'll just report some of them, exactly. So it's a good thing to have as a standard, because it's not going to prevent you from compiling. It's just going to let you know if there's potential problems. And then -c, that is the option that just causes it to be translated from the source code to the binary, and it doesn't get linked. So the linking is where, if it's just a single file, it gets turned into an executable. Kind of gets like stuff wrapped around it so that it knows how to run on the computer. Or if you have multiple files, when you link them, then they can suddenly see all each other, and then they all get combined into an executable. So it's two different steps. And I guess I would say the two different steps are, one is compiling the source code into the binary code. Okay? You can't run those. It's just something that the computer can read. It can understand those. But then when you link them, that's when it all gets combined into an executable that you can actually run. So it's two different steps. A lot of times, it'll just all happen at exactly the same time. You won't see it. It's hidden. But if you use that -c, you can break it out into the two different steps. Exactly. Yes, exactly. Yeah. Sometimes you just want to compile, if you have like a really big code, sometimes you just want to compile part of it um, and not include it into the rest of the code. Or maybe you want to mix and match parts from different codes. Like I compiled this 10 days ago and I compiled this yesterday. Um, they're both fine, so now I'll just link them together and run them. So it's just a way of organizing the building of software. It's not something that you necessarily have to do. You can always just do GCC and then include all of the files that go into an executable. But sometimes it's easier to break them up break that up into separate steps. That's not something. That's something you get a feel for after you've worked with it for a little while. It starts to make more sense. Yeah. Dot slash. Mm-hmm. That should work. Is it? So now it's compiled. It exists. Or it's not. Yeah, now it's been compiled into this error.o. Yeah. So, well, you can't run it because, like I was just telling him, if you have that -c flag, all it did is translate it. It didn't put the wrapper stuff around it so that the computer knows how to run it. Right now, it's just source code.
So it would just we would just want -o.
Yeah, if you wanted to just call it that and run it, yeah, you could do that. If you didn't want to break it up into two different steps. Now, from this step, though, you can do GCC. And then we can just do error.o, actually. I think that should work. And now that produced a file called a.out, which you can run. Or we could have had the -o and called it whatever we wanted. -o just names whatever comes out of there. Yep, but no space. Yep.
Any other one? Like, what is the difference?
Which one?
And like
Oh, we just made it. We just skipped some of those. So you could throw in a -w all there if you wanted to. Print all the warnings that you see. So it doesn't have any warnings in this one because it's correct, and so you won't see anything there. Yeah, it's just a flag or option that says, hey, output the compiler's, the file that it produces, name this. -c is just compile. Yeah. If you don't have that, then it'll link it. Run. Yeah, the executable is. It's the binary code, but it's also set up so that you can do the dot / first code. Yes. Yeah. Mm-hmm. The -o. -w -w all. So it means print all of the warnings that you see. If you don't have that, it won't print every warning. And it's just an option. You don't have to do it. But sometimes it's nice because it tells you, it warns you of potential problems. Yes, you can. Yep. Mm-hmm. Oh, how's VI? I think it's quit.
Save change or no? No, it doesn't matter. Not
Um,
Is it semicolon and key?
just colon. You might have to do escape first.
Yeah.
Yeah, I don't remember
Okay, so yeah, so when you
keystrokes.
to type something in, you hit I first, and then after you type in the text that you want, then you hit escape, and then you save it. You type colon WQ exclamation point. So that will save the file.
What about
Type Q.
You have to be escaped for that.
And then hit yeah. Hit.
Yeah. Yeah, I always did Emacs. Yeah, I don't even know the keystrokes, the names of them. My fingers just go to them. Okay. Yeah. Oh. Um, you know, Jason, difference between Objective-C versus C. Objective-C a different language entirely? Oh. Okay. What about them? Right. Yeah, you got to come in with your own. Yeah, that's the problem with software that costs money. I don't know. I think it's expensive though. I have to ask the guy that. Yeah, did they any of them have the distributed computing one though? Okay. Yeah. Okay. Does anyone want to get started again, or do we want to wait a few minutes? How's get started? All right. So I move on to things like comments, keywords, identifiers, and variables. Kind of the grammar of C. So comments, a new line. This one is rules.c. We'll call this file that. You're welcome to cut and paste this one if you want to into your editor and compile it and run it. It'll probably be good practice, just so that you kind of remember how the workflow works. At the top here, this is the actual top of the file. When you cut and paste, you would start at the top. You have a / star, and then that gets closed with this star /. And then every line in here, you start with the star. And all this stuff does, these stars and slashes, it tells the compiler to ignore those lines. And it's just for commenting your code. And you might not think that's a big deal, but that's one of the biggest challenges with reusing code and people correcting mistakes in old codes is things not being documented properly. So in the end, we're not going to focus on anything like that today, but it's something to keep in mind. It makes a big difference in terms of your code being reusable and of interest to other people. Then the next line, again, is this preprocessor directive. Include stdio.h, which has the functions printf defined in it, as we recall from our previous examples. And of course, we have a main. We always have to have a main. And then we have the braces, the opening brace and the closing brace. And all of these statements in here belong to the main function. Again, we see our old friend keyword return space 0. Yeah. Exactly. Yeah, we will see that momentarily. Good catch. So, yeah, we do this printf multiple times here. As one of our participants just said, there's no \n. And so what you'll see is everything just kind of gets mushed together onto your screen. There's no new lines being introduced. And this is not typically how you want to print out text from your code. So to change this, we just add the \n to each of our print statements at the very end. And that just tells our compiler to start a new line every time it sees one of these characters. I mean, \n is just really another symbol like everything, like a C or an E or whatever. It's just a return, basically. Start a new line. And if you do that and compile it and run it, you see you get new lines for each one. Looks much better, much cleaner. So this is just a do-it-yourself activity. You can learn the different ways that you can print and format values for different data types. And this is referring specifically to the printf statement. So if you want to print a string or a character, you have to do it slightly differently than printing an integer or a float. And we'll see a few examples of that throughout the slides. But there's a reference at the bottom of here that you might find of interest in the future. Printing is one of the most useful ways of just quickly debugging your code or making sure that the results look correct. And it'd probably be worth your while to check this out and at least get familiar with how the printing works. So this slide is a lot of the C language keywords. This is kind of like the vocabulary of C. And this is actually a lot of it right here. In most code, you don't use anything except for these keywords. So there's not a whole lot to it. You can do incredible amounts of work with it, as you've seen all the so much different code, operating systems, Python, R are written from C, built up out of C. And I'm not going to go through each of these in detail until we get to them in the slides. But you have different categories of keywords like storage class specifiers, and they kind of describe where a variable can be seen and how long that variable lives throughout the code. Structure and union specifiers, really no one ever uses union in my experience, but structure is just a way of combining different basic data types into more complex data types. And I think we will have time to see some examples of that. Enumeration, we'll see an example of that. It's just a way of specifying several variables. Type specifiers. These are different types. I'll talk about these a little bit. Characters, like any symbol A, B, C, 1, 2, 3, any punctuation marks. Double and float are both like your real numbers, like 3.14159. Doubles just twice as precise as floats. Int is an integer. Long and short, they can be in front of double, float, or int. And so you can modify a float. I think you can make a float or a double from a float by putting a long in front of the float. So it just makes it longer. You can't really go larger than double within the standard C syntax, or more precise. And you have signed and unsigned, which work the same way that you would think they would. A signed integer allows you to have negative values for the integer, or positive values for the integer. The same for doubles and floats. Unsigned just means that there's no negative values. And then void is kind of this weird type that it's not a type. It's just basically machine code. Now, the reason you have these types is that really in the computer, it's just ones and zeros for every variable. But applying a type to it, that allows the computer to interpret those ones and zeros. So you might have a pattern of ones and zeros that is identical to, for a variable that's identical to another variable's pattern. But when you put them through the filter of the type, then the computer will see them as like an integer or a character. And I think we'll actually see an example of that in a moment. And type qualifiers I won't talk about just yet. Control structures, these actually are pretty sensible names. If else, do while, for break, continue. We'll see some of these guys. And their names are relatively intuitive. An operator, Sizeof, I think we'll see an example of that. Just tells you the size and the number of in terms of bytes of your variables. And I don't really care to talk about deprecated keywords. And I don't think we'll go over these reserved words at the bottom here. So what are variables? They're basically information storage places. So the computer associated with the variable is an address in the memory. So it's just the location that the variable lives in memory. And also the value that's in that address. And also, it can be the number of bytes that that address takes up. So when a computer sets up space for, or wants to hold a variable, it's got to find a spot for it, and then make the space for it, and then initialize the values in that space for the variable. And you'll see lots of this coming up soon. You can contain strings, characters, or numbers. They're variables, so their values can change while the program's executing. Except for there's one type that doesn't actually. I think we'll see one of those. And you have to declare every variable before it's used, and it has to have a data type associated with it. Otherwise, the computer doesn't know what to do with it. So, yes, they must have a value before you can use them. Yeah, because it doesn't have a value. The computer doesn't know what's in there. I mean, well, that's a good point. Some variables are, but it's not reliable. It'll be different from system to system. So maybe it will be zeros, but maybe it'll be a bunch of junk. And so you really want to initialize it before you use it. Stay out of trouble. Okay. Yeah. Yeah. So the question before that I was just asked is, what happens if you try to use a variable that's not initialized, and it's not defined for most variables in C. So it doesn't mean that it'll be wrong, but it means that it won't be reliable. You don't know for sure what it'll do. So what is a data type? That it's characters, doubles, etc. They specify the type of data that a variable holds. It allows the computer to decide or to determine what those ones and zeros in the variable mean. There's three different types, main different types of data types. The built-in ones, like I just talked about. Then you can build your own using structure, or the struct, union, and enum keywords. And we'll see an example of struct and enum later on. And then also derived ones. So array is a special thing in C, which is a series of identical data types that are contiguous in memory. And so the easiest thing to think of is like a vector that can be represented by an array. A function has a type. It's not necessarily data in it, but it has a type. And a pointer is an address to a variable. And we're not going to go into pointers today unless we have time. They're useful. They take a little while to get a hang of, but a pointer does have a type. It is the address of a variable of a particular type. That's all I'll say about that for now. You guys have already seen an example of a function and its type, so the main function always has to be an int. Let's see. So different platforms will have different ranges that types can take. So an integer, like on a 16-bit platform, minus whatever to plus whatever, 32,767. And that's just the number of, I think it's like 2 to the 15, plus you have 1 in front of every, or 0 to decide if it's a plus or minus variable. And then 32 is much more, and then we actually work on 64 bits, so we even get more. Yeah, unsigned integers. My understanding is that it's used as an additional one, so it can be bigger. I'd have to double check that to make sure, but I think that's what it does. Yeah. Oh, I was just asked if for an unsigned, if that extra bit just allows you to have a bigger number represented by the integer. And I believe it does. I'd have to double check. So an identifier is just the name of your variable. Every variable needs an identifier. So my variable's name is X. X is the identifier, or A, or B, or whatever. Usually you want to give a variable a name that makes sense so that when people look at your code, they understand what it helps them understand what it does. Exactly, yeah. It helps a lot with code reusability and just the robustness and maintenance of code is giving variables sensible names that lend some intuition to the purpose of them. The next bullet, the valid identifier is just a sequence of, you can call it whatever. The only thing is it can't be like punctuation other than underscores, and it can't start with digits. That'll confuse the compiler. But you can have a C9 or C9 space slash or C9 underscore D or whatever. And keywords can't be used as identifiers because once the compiler comes up against those, it won't know what to do. It'll think it's a keyword. So variable declaration. This is the statement that defines a variable. It tells the compiler, hey, this variable exists. Gives it a name, and then it stops there. It includes the specification of the data type and also the name or the identifier of the variable. So for these examples, int number 1, float number 2. And you can also declare multiple variables in the same statement. Remember, statements are ended with a semicolon. And this is how you do it in x, comma, y, comma, z. Yeah, like I said, sometimes the data can be signed or unsigned. And like I said before, can be used to represent positive and negative values depending on if it's signed or unsigned. Yes? Mm-hmm. So I was just asked if, for this last example, signed double temperature, if you left the signed off, if that would change anything. And no, because that's the default. So there's no reason to really to have a signed for a double. That's what the compiler will do automatically. But maybe sometimes that would help in just description of the variable, or might be a good programming practice in certain instances. You can actually assign a value to a variable when it's declared. And this, the line between declaration, definition, and assignment it's a little fuzzy, but at this point, let me just put it this way. When you declare a variable, it makes just lets the compiler know that that variable exists. When you assign something to that variable, the compiler actually makes space for that variable in memory, and it gives it a value. So in this case, int x equals 10, and then of course semicolon. So you always need that semicolon. Some other examples here, just character x equals a. So a character is just a single, like I said, a single symbol, letter, number, whatever. Double x equals all this stuff. And then another example, float x equals 10.11. So you can see that it's the same name. You wouldn't want to have, actually you can't have the same name for different variables of different types. You would have to change the name for each one. Yes. Yeah, I was asked if x, this double x, is outside the range. That's really a double is a floating point variable, so it's a number of significant digits that it can represent, not just the magnitude. So that decimal can move around, and you can use like scientific notation to interpret it. Yeah, you can't use void to declare a regular variable. Void doesn't really mean anything. You can use it as a return type of a function if you don't want your function to return anything. So if you just want your function to print something, but not necessarily give a value back, you can use that. Let's see. Okay, so this is the last slide for this first session. It's an example of updating variables. The source file is myage.c. Again, you're welcome to cut and paste this, compile it, and run it. See how it works and what it produces. Again, we have our include the printf function using stdio.h, and of course the main function. And then we declare the variable age, let the compiler know that this variable exists and it's of type integer. And then we'll assign the value of 10 to age. And this equal sign is the assignment operator in C. Then we've got a this. Then we got our printf statement. This one's a little bit different than some of the printfs that you saw before. And that's because it has an argument now. It has an argument of type int. The argument's name is age. And it'll appear in this string when it's dumped out to your screen where you put this %d. So printf will print values of things, or it'll format the type of the variable, and you have to use %d, for instance, for an integer, or %f for a float, %s for a string. And then in the next line, we change the value of age. Okay, we can print that out. Okay, we changed what that value is in memory. And then we can actually add something to age and then assign it to age. And then again, we can print out that. And as always, a return 0. And this is what you should see at the end after you compile it and run it. Yeah, so I was asked, what if you want to print multiple variables? Printf is really neat in that it's one of these types of functions that can accept what they call variadic arguments, or basically any number and combination of variables. So you can have 1, 2, 3, 100 different arguments to printf. And all you would do is have another %d. And so the first argument will go with the first one appears, the second where the second one appears, etc. Yeah. Do we see single? Single will not work. It won't know that that's a string. Oh, before this slide? Oh. Not for our purposes. There is a difference. I have to look up what that is. Do you remember, Jason? Okay. Okay, I was just asked if there's a difference between using single quotes, like in the character x equals a example, and using double quotes, like in all the printf statements that we've been doing. And we're going to say for now that the single quotes are for characters and the double quotes are for strings. I believe that's correct. And then the last slide here just has some references that people might find useful that are starting out with C. And so that's it for session 1. Move on to the next session as soon as we get this set up and people are ready. Now's a good time for any additional questions. If anyone's stuck on anything, or are we all ready to continue? Okay. Might stop again around 2 o'clock, but see how far we got. Get this set up. Oh. Yeah, the in the corner keeps popping up. We'll get started again as soon as we sort out this. Are we good? Okay, well, I'll get started again here, and then we'll stop if we need to for the technical difficulties. But looks like we can. Uh-oh. Okay, so the last slide, or the last lecture, you guys all remember because we just did it. Went over keywords and comments, understanding errors and variables and data types, and of course printing to standard outputs and compiling and running. In this next session, we're going to talk about typecasting, which is converting a variable from one type to another. The scope of variables, which is how long a variable lives in the program. Constants, operators, like plus, minus, comparing two objects, and also some standard I/O functions, ways to get stuff from the command line into your program and print stuff out. Let's see. So this is our example from the last one because we just did it. We'll pass by that. Now, what they call typecasting, you can change a type of a variable to another type of variable. You can change an integer to a double, for example, or vice versa. You can really, you only want to typecast when it makes sense. You can get into trouble if you just do it willy-nilly, but we'll see a few examples where it does make sense. Let's see. So yeah, you just put the data type in parentheses in front of the variable to change its type. So here's an example code. We initialize variable a equal to 65, and its type is double. And then we declare variable b as a character. And then we say variable b is equal to variable a, but we're going to first convert this double 65 into a character. That's exactly what this char in parentheses means. Now, why you would want to do this, I don't really know. But if you, there are instances where you might want to do this, like converting a double to an integer or vice versa. But when you feed this then into the printf statement, print variable a to double, and in printf, that's designated by an lf, long float. And variable b, this %c is for character. And the output of this will be variable a is 65, and variable b is a. And that's just because in the computer, 65 actually represents a. If you go and look at what the those ones and zeros mean when you convert it into a character, you get a. Like I said, this is not a particularly useful example, but somewhat informative of how typecasting works. Yep. You should get an error. It should get mad because you're trying to assign one type to another type, and that's something that the compiler can understand. And so I was just asked what happens if you did not have that character there and tried to assign variable a, which is of type double, to variable d, which is of type character, and you should get an error there. That should make the compiler unhappy and scared. There's no string type exactly. A string is actually a array of characters. That's how it gets defined. In this case, as long as your string was length 1, I think it should just give you an A again. If it was larger than that, then you would, when you tried to print it out, I think you would still just get A. It would just ignore the extra slots that come later, or that are part of it. Yes. Yeah, so I was asked if you can, instead of splitting this from character var b and var b equals character var a, instead of having that as two separate lines, could you just say character var b equals character var a? And yeah, that's totally fine. There's nothing wrong with that. So this next example looks at implicit type conversion. And basically, the compiler is smart enough, or at least it's a simple enough operation that it can convert something like a double to something like an integer, and just do it automatically. Now, if it's what you want it to be doing, that's another question, but it won't raise an error, and it does have a defined way of doing this. So in this example, var a is a double of type double. Initialize var b as type integer, set it equal to 2. then we say var c is equal to 9.34, and var c is a double in this example. Then we try assigning var b, which is an integer, remember, to var a, and then we assign var c, which is a double, to the integer var b. And then we print it out. Again, hopefully you're starting to get familiar with how the printf statement works. 3 arguments, var a, var b, var c, and then %lf for double, %d for integer, and again %f for, or lf for double again. And down here we see the output. Var a is 2.000, because it converted the integer 2 into the double 2 automatically. Now what happens when you convert a double is that everything that comes after the decimal point, or a double to an int, is that everything after the decimal point just gets dropped. So this is not usually what you want to be doing, but it is how it works in the compiler. This will always happen. It'll get, the 0.34 will be dropped, and you'll just be left with an integer 9. And then, of course, var c is just a double, and it gets printed out as a double again. So we call this conversion from int to double implicit, because you didn't tell it to do that. It knew how to do something there. It knew how to do the conversion. Okay. Scope of variables. This is definitely an important topic, and it can take a little while to get used to and get familiar with. Like I said before, scope is kind of the space within the program that a variable exists, how long it's like alive or can be seen or accessed. A variable can either be global or local. A global variable is just defined outside of any function. It can be seen by all of the functions that are in a particular program file, in a particular source file. Then a local variable can only be seen in the function that it was originally created. And we will see examples of this. A local variable can also be qualified as static. This is maybe I would say it's a slightly more advanced concept. It's not totally necessary to get someone up and going in C, but it can be useful, certainly, if you're comfortable with it. And all it means is that once that variable is initialized, it stays in memory. So for a usual variable, once you enter a function, if you declare that variable within the function, as soon as you leave the function, that variable is gone. It doesn't exist anymore. But if it's a static variable, then it'll still exist when you come back to it. So if you set its value equal to 10, and then come back to it later on, its value will still be equal to 10. I think we'll have some examples of this so that you can get a better feel for what that means. Register, it's kind of this type, or this scope definition is sort of deprecated. It's not real commonly used anymore. But what it used to do is make sure that the variable stayed in the machine registers, so closest to the chip. So if you're going to be reusing a variable over and over again, it could be faster to just be accessing it from the registers rather than going out to memory to get the variable every time. And it was just a way to guide the compiler. And it never forced the compiler to put the variable in the register. It just suggested to it that if you can do this, it might be faster to do this. So constants are, it's a pretty simple concept. Once their value is assigned, they can never change. There's not really any reason that you would ever have to use the constant. But it's convenient because it helps you not make mistakes. It helps you not write over the value of a variable. So in this case, like the value of the exponential constant double E equals all this stuff. Throughout the program, that will always be the value of E. If you try to assign to this value or something else to this variable, you'll get an error and during compile time. And then macros are another convenience and time-saving concept. So, for example, this is a preprocessor directive, pound define max records 100. So everywhere max records appears in that file again, it'll just be replaced by 100. It just gets substituted, and it just helps save time. It helps you to avoid hard coding the same value at a whole bunch of places. And yeah, it can be used in wherever a constant can be used. Enumeration is, yeah. Yeah, I was just asked if a macro is always an integer, and they're kind of weird. It's actually, it doesn't have a type. It just goes through that file, and anywhere it sees max records, you don't have to have, you could have an S there instead of 100, and it would just substitute S wherever max records was in the file, and then it'll go through and compile it. So it's almost like changing the source code before it even gets compiled. Does that make sense? I don't remember if I said this. I was just asked if max records has to be 100, or if your macro has to, or if a macro has to be an integer, and no, it does not. Enumeration is a list of constant values. Sometimes it's just convenient to, you never really have to do this, but it's sometimes a convenient structure. In this case, enum, boolean, no, and yes. And so throughout your code, you could say if this variable equals no, or if this variable equals yes, do this or do that. Yeah, and expressions that contain constants are just evaluated at compile time. Space is made for them in memory. It's part of the source code. And let's see what's next. Okay, so operators. It's how we do a lot of our useful things, especially in scientific programming. Addition, subtraction, multiplication, etc. This is a pretty comprehensive list of all the operators here. I'm not sure of any that are missing, but you have arithmetic operators, or mathematical operators that we're all familiar with. We'll see what plus plus is called the incrementation operator, and minus minus is the decrementation operator. We'll see what that means in a moment. Relational, which are ways of comparing values of different objects. Equals, equal sign is equals, not equals is, exclamation mark equals is not equals. Greater than, less than, just like how you would think they work. Greater than equal to, less than equal to, just how you think they work. Then logical operators, we have not a. So the exclamation point typically means not in C operators. And then a, ampersand, ampersand b means a and b. And then, I don't even know what you call these lines. Call them pipe symbols. A pipe symbol, B is A or B. Next. Won't go through these. We'll see these when we come to them, the member and pointers. Wouldn't necessarily call size of an operator, but it does measure and return the size of a variable. It has a very specific purpose. And bitwise operators, I don't think we need to go into those right now. It's just ways of actually adding or multiplying ones and zeros at the zeros and at the level of zeros and ones. So increment and decrement operators is the next slide. Plus plus I means add one to I and then use it. I plus plus means use I and then increment it. So plus plus I, first we set I equal to 6, declare a variable j, and then j is equal to plus plus I. So I gets incremented by 1 and then assigned to j. So j will have a value of 7 after this. Or we can do I plus plus, and in this case, j will get the value of I, and then I will be incremented. And the same works for the decrement operators as well. What if you use, the question is, what if you use the increment operator on a floating point variable? I'm not 100% certain. I think it might just add 1, but I don't recall. I've never done it, so I don't know how useful it is to do that. Okay, so precedence of operations. Fortunately, in C, this usually works how you learn in school, associative and commutative operations and all that. So in this example, integer, we declare a type, a variable total of type integer, and you can read this next line, total equals 100 minus 25 times 2, because multiplication has a higher precedence than subtraction. And we print it out, again, with the, not sure why there's a dollar sign here, but the %d indicates the total. And then if you have the parentheses in here, just as you would intuitively expect, then the subtraction happens before the multiplication. So here's an example of a Sizeof operator that we keep seeing pop up. And this can certainly be useful sometimes. So we have a variable C of type character, variable X of type int. And then we're going to look at the size of, where the argument of size of is the variable name. And then it'll print out the variable, or the size of the variable in terms of the number of bytes that it takes up. So the size of a character is a single byte. That means it's just 8 bits, 256 different types. Size of variable x, which is an integer in this case, is 4 bytes, 32 bits. The size of a double would be 8 bytes, 64 bits. Yeah. Well, that's 32 bits, and 1 billion, on a 32-bit system, yeah, you could represent 1 billion with 32 bits. Yeah, 2 to the 32, and that's what that. Right, and I think you can add the long in front of it and then make it like a long int. Or if it's unsigned, you probably get additional bits that you can work with. Yeah, I'll skip this note. We'll see this later. A character is different than a string, like I mentioned before. So now we'll look at, we've already seen some output, the printf statement, and you'll see at least one more function that outputs stuff from your program. But the input we haven't seen how to get stuff into your program yet. So we'll see some simple examples of this. Now this one might actually be worth your time to cut and paste, compile and run. So this one is called readInput.c, this example. And what happens is we declare a string, which is a place that we're going to hold our input. In this case, it's an array of length 50, where each element in that array is a character. Don't worry about the exact definition of an array yet, but this is how you declare a string in C. Then a printf statement like we're used to. This flush isn't strictly necessary, especially in this example, but it's good programming practice. It's just a buffer that holds stuff that comes out of programs, and this just cleans that out before your program is run. And then this next function is scanf, which is scan formatted input, basically, you can think of. And what this does, it kind of works the opposite way as printf. So it'll take something from the keyboard that you type in, and then assign it to this string, my name. And then we can print out that value. If people want to give this a try, I'll wait just a couple of minutes for you to do that if you feel like it. Actually, I'm going to take at least a 5-minute break here, and it's 2 o'clock now, I'll be right back. We'll work through this and see if anyone has questions.
or is that? It's to help you. It's like, oh, you get this. Yeah. So you fantastic those. Well, you can actually. So if you have like a text argument every field, errors that show up there, they should show up in the field. See it, can see it. Yeah, that's it.
Yeah, that is probably what's happening there. You can change that. You can change it to exactly how it works with an example later, like a regular expression type thing where you kind of tell it to read up to this point. But yeah, you might break on a white space. Actually, I think it's white space in front of this percent. I just wanted to warn anybody who's trying to do this online. In the scanf function, there's an ampersand in front of my name, and it turns out that on at least on Ubuntu, it doesn't like that, and you have to remove the ampersand. I couldn't tell you why, but in this case, for that version, it didn't like it. Yeah, so this 100 here, basically, I'll describe arrays later. But basically right now you can almost think of it as a vector of 100 elements, and each element is a character, and so you can build words out of that, and that's what they call a string in C. Is everyone here okay with me moving on? Okay. So I described all the different statements here. Again, you don't really have to worry about the F flush. It's not particularly important to what we're doing. So a little more information on scanf. This guy is defined in, I believe it's in stdio.h, as we can see on the previous slide at the top, just the same place that printf is. Um, it just reads information from the keyboard, input from the keyboard. The first parameter is going to be a type specifier. Just like with printf, it'll be the same kind of thing. A %s is a string, %lf is a double, %d is an integer. And yeah, they list some of the type specifiers here. %c for character, etc. You can also do things in terms of octal and hexadecimal numbers if you want. And then the second parameter is the address of the variable, which apparently in Ubuntu doesn't work quite the same. But it's the, again, my name is the string variable for storing the value, and the ampersand, anytime you see that in C code, that's actually giving you the address of whatever that variable is. So it's where it's located in memory. And some functions take the address as, or yeah, some functions want the address of the variable as the argument, and some just want the variable itself as the argument. Get_s is a function that people don't really use anymore, but it also works like scanf. You can use it to read keyboard inputs, but it's, if you try to run something with it, I think we will in a minute, you'll get a warning, and they call it keyboard overflow, and it's somehow you can, it doesn't, somehow you can insert malicious code into someone else's code. And so basically just don't use get_s, except for the 1 or 2 examples we use it in this in this training session. Put_s works a lot like printf. It's just simpler, doesn't take any arguments, and it just dumps whatever you have, whatever string you give it, slaps on a /n, a new character, and prints it out to the screen. So it's just like printf, but easier, but doesn't have any, not as flexible. Get character is about as exciting. You can read a single character from the keyboard. It'll again give you the little pause and S, and you got to type your character in. And then put character displays a single character on the screen. Or C is a character constant or a variable name. Yeah, so in class here we already talked a little bit about string variables. So you can, in the case of numerical variables, like you saw, you can just say int x equals 10, and that's just fine. But if you want to assign a string to a character array, let me just use that terminology for now without defining it too explicitly. It doesn't know how, because this my name is actually composed of 50 different elements, and then the string that you're trying to give it is composed of 4 different elements. It doesn't really know, the compiler doesn't know how to assign that variable immediately, like it does in the case of a double or an integer. And so there's different functions that come with the C compiler that helps you do these assignments. Like in the case of scanf or get_s, that's from the keyboard input. Or in the case of string copy, that's something that you can do within the program itself. And I think we see an example of that next. String copy, it's defined in the header file string.h. And so anytime you want to use it, just like printf, you've got to add it to the top of your file. And again, it just copies the value of one string to another. So here's our string copy example. Again, we have stdio.h like almost always, and now string.h. Just exactly the same way you include those functions. We have a string, I'll call it, which is an array of characters of my name, and also one called myname2. And then just a character C. And then we can copy, using the string copy command, this string, in this case re2, into my name 2. You can, like I said, you just assign it using the equal sign. You have to use this function. And then you can continue to do that. You can copy my name into as many other strings that you defined. But you can assign, because C, a single character, you can assign a single symbol to it, because it's not an array of characters. So the compiler knows exactly how to do this immediately. And then we just have our printf statements again. And this is the output that you would get, just probably as you would guess. So this first bullet point, how would you use scanf? That's going to be just like when you think about how you use printf. It's just the different types of variables that you would read in. If you use %s or %d, etc. Now this following, the second bullet point here, is this statement correct? How many people think this one's correct? How many people think it's wrong? Okay. Yeah, so because we've got 2% defined here, a %s here, and a %s at the end, it's not going to work properly. Red is not like going to go to both of them. It'll probably go to the first one, and then you'll get junk in the next one. It's probably just not going to be defined, and you don't know what it's going to do exactly. Won't necessarily break your code, but it won't give you sensible results. It's not guaranteed to give you sensible results. And yeah, I will just say for this last one, you would want a D because it's an integer, %d. And then typically you want an ampersand here before my integer number. And that finishes the second session. And again, these are the same references as before. And I'll move on to the third session here in just a moment. If I can. Yeah, I'm not sure what it wants. I'm going to wait about 3 minutes to get started again. Okay. Start the third session here. Hopefully this gets a little bit more interesting because we'll actually be able to do something with what we've learned rather than just printing stuff out to the screen or reading in stuff from the keyboard. Just a quick recap there. Last thing we talked about was I/O functions. We'll talk a little bit more about I/O functions, slightly more useful thing to do with them here. So keyboard input is always read as a string, and the integer 25 is different from the text 25 that you enter into the keyboard. Like we saw when we converted A, which was the variable A, which had value 65 to a character, and it printed out A. It's the same thing if you try to do that with just sending 25 through the keyboard to your program. It'll think it's the text 25, and I don't know which symbol that is, but that's what it'll think that it is. So there's actually a function in the standard C library that converts, kind of has like a map between the numbers and the letters, and it'll convert 25 to the actual. In this case, it'll interpret it and make sure that it's interpreted as an integer, and that's defined in this header file stdlib.h. Again, that works just like stdio.h or the string.h. There's functions in here that you can use if you include that at the beginning of your file. Some other conversion functions are at this link at the bottom. This link is still active as far as I'm aware. I checked it last week. So here's an example where we convert an keyboard input, which comes in as a string, and we'll convert it to an integer. You're welcome to cut and paste, compile, and run. It's going to be really similar to the previous ones, where you give it some keyboard input, and then it'll print out something at the end. So again, type integer variable name A is what we start with. Then a string, enter age. The string is size 8, so there can be 8 letters or numbers in the string. Then printf, it asks how old's your friend. Flush, we'll just not worry about that. And then get s, which is that really dangerous function that you're not supposed to use, which gets the keyboard input, but it's really easy to use. And then a to I, which get s, get the string, it gets what you put in the keyboard, puts it into enter age, and then a to I converts that string to an actual number. So you assign it to this integer type age. Then when you print it out, again, you have to use %d because age is of type integer. And this is the output that you should see. We saw that already. Okay, now we'll move on to control structures. There's 3 main types of control structures. Sequence structure is a sequence of statements, and that's exactly what you've already seen. Integer age is the first statement, and the next statement in the sequence is character, enter age, and etc. So that one you're familiar with already. Selection structure allows you to make decisions throughout your code. So if something equals something, then let's go down this branch of the code, or jump to this other part of the code if this is false, some statement. And then loop structures, that's one of the more common things you'll see in scientific programming. It just allows you to do the same thing over and over again for without actually having to write it out. And we'll see a good example of that in a minute. And we'll ignore this note for now because we haven't gotten to that yet. So here's an example of the selection structure on the next slide. The if-else statements. You'll see this one a lot. And so this first example here, if A is greater than B, that's what this means. If is a keyword in the C syntax, and then you have some conditional, what we call a conditional, A greater than B, and that's always in parentheses like this. And then everything that happens if A is greater than B is contained in these braces. So if A is greater than B, then we'll set Z equal to A. If A is greater than B, in the next example, Z is equal to A. Or else, if that's not true, then we go to else, and then we say, okay, Z is equal to B in this case. And else, again, is a keyword in C, and it contains everything that belongs to else is in these brackets. And then there's also what they call the ternary operator. It's the only operator that has 3 different arguments. And you can read this, if A is greater than B, then A. If A is not greater than B, then B. So Z will take on the value of A if A is greater than B, or else Z will take on the value of B if A is not greater than B. So it's exactly equivalent to setting the maximum of A and B equal to Z. Does that make sense? Ternary operators were kind of weird for me when I first saw them, but basically how you can read them. It's exactly equivalent to the second if-else statement. Let's see. So you can combine conditional statements into logical expressions. So what this means, this first example means if temp is greater than 75 and temp is less than 80, print F, print this thing out. So if temp is between 75 and 80, then do what's inside these brackets. And then this is if value equals E, or is what these two double pipe symbols mean, or value equals N, do the print F exiting the program, or else print F in the program. Yeah, you could use it. It would just return. I was asked, can you use the ternary operator in combined logical expressions? And you can. You'll just get it'll just evaluate to what that ternary operator evaluates to. Now, if it makes sense or not, that depends on how you've set it up. But does this make sense to everyone? Okay, now we'll look at the decisions. Yeah, so we've already seen the if-else expression combination. If the expression is true, then statement 1, else statement 2. Now you can actually do this for multiple arbitrary numbers of conditions. So what this means, if expression 1, then statement 1. If expression 1 is false, then we go to the else if expression 2. If expression 2 is false, then we go to statement 3. So statement 3 in this case is almost like the default value. If everything's false, then you'll end up with statement 3. And you can do actually exactly the same thing with what they call the switch statement. It'll test this expression, switch. It'll evaluate the expression in the parentheses after switch. And then it'll go through this list that comes after after there and find which one the expression corresponds to. So maybe this first case is A, and the second case is B. Expression A is, if the expression evaluates to A, then it'll go with statement 1. If the expression evaluates to B, it'll go to statement 2. If it evaluates to nothing, or something that's not in this list, then it'll just go to the default. Exactly like the if, else type of statement. And you can have as many of these as you want, as many as you can keep track of. So here's an example in a real code. This is a snippet. There's a few more lines. They just don't fit on the slide. And they're not clear. Or the text is too small if you add them. So we will define the character C, and then input that value from the keyboard. And then we'll go through all of these statements here. If C is equal to 1, then print this first statement. If it's equal to 2, then the next one, 3, 4, etc. And then it'll eventually come to else at the bottom, which is the default. Yeah, so this is what you would see if you compiled this and ran it. It'll print out these first 4 things, then you'll enter in the value, and okay, hot dog, and that'll be expensive hot dog. And you can do exactly the same thing then with the switch function, switch expression. Yeah, this is exactly the same as the last one. And I should mention, all of these codes are available if you are on Stampede. You can go to the train. It's called the train 00. So you would do a tilde train 00. And in there, there's a whole bunch of like type of lab exercises and everything. But the stuff that corresponds to all of these lectures, it's called Training C. And there'll just be a directory in there, and you can copy that directory into your own directory or onto your own computer. And all these examples are in there. You can compile them, run them, etc. If you have any questions about how to get access to that, just email me or whatever you want to do. Okay, loops are, like I said, one of the most relevant things for people in science and doing scientific computation. Lets you repeat a whole bunch of steps and statements over and over again without having to actually type it out. These statements will be executed a particular number of times or until something is true or until some condition is met. There's 3 types of loops in C. We have for loops, while loops, and do while loops. While loops and do while loops are almost the same. You can pretty much get all of the functionality of any one from any of the others. It's just a matter of convenience and clean code writing to use one versus another. For is definitely the most common, then while, and then you'll occasionally see do whiles. So in a for loop in C, we have the keyword for, starts off with that. Then you give it a start value, usually an integer, like integer I equals 0. Then some end condition, which that tells the loop when to stop. So stop if I is greater than 10. And then the stride, which is how much I increments every time it goes through the loop. And every time it goes through the loop, or every time this loop gets executed, the statement will be called. And I'll show you examples of this in a minute. But if you have multiple statements that you want to execute for your loop, you want to use these brackets here. And that'll tell the compiler, hey, all these statements belong to that particular loop. So here is our first example of a loop. Again, our old friend stdio.h and int main. We define an integer I, and now we'll use I to control this loop. I will start off equal to 0. As long as I is less than or equal to 10, this loop will keep going. And then we'll say every time the loop is executed, increase I by 2. And so if we copy and paste this, compile it, and run it, this is the output that we'll get. It'll go through the loop, printing this each time until I is greater than 10. And so if you messed up and didn't increment I every time, like in this the third field here, loop would just go forever, and you'd have to just kill your program in some way. So next example, very similar, but here we're adding numbers together. So we have our integers I and sum. We'll initialize sum equal to 0. We can't use sum unless we've initialized it and given it assigned it a value. And then we'll start at I is equal to 1. Execute the loop, and then test if I is still less than or equal to 100, and then we'll increment the value of I, and then we'll repeat and go through the loop. And so this is adding the first 100 numbers, and this is the value, the output that you should get from here. And I already mentioned this earlier, but you can declare variables on the same line and see, like in the case of int I, comma, sum. Yes. Okay. I don't know, do people want to try to compile this one and run it, or feeling pretty comfortable with it in any case? Well, move on to the while loop then. While is a little bit simpler than the for loop in some ways. You don't know how many times you actually want to run through the loop, you can use the while, and it'll just keep executing the statement over and over again as long as some condition is true. Now you could replicate a for loop doing this by incrementing some integer in here, and then if that integer is greater than a certain value, then break out of the while loop. Yeah, so you can actually modify this statement from within the loop itself. Yeah. So we'll show what that means here in this next example. So here's our whileloop.c example, declaring counter and value both of type integer. Then we initialize those two, value equals 5 and counter equals 0. And this is just like a for loop in functionality. While counter is less than value, we'll print out the value of the counter, but we'll use the increment operator with counter to increase its value each time the loop gets executed. The first thing that will happen after it enters the loop is it'll increment the value of counter, then it'll print out the value of the counter, and then it'll test if counter is still less than that value. So you could do this with a for counter equals 0, counter less than or equal to 5, counter plus plus. It's the same functionality as a for loop. Do whiles are a little strange, not totally necessary, but maybe convenient in certain instances. basically, it's just like a while loop, but you're guaranteed to do the loop at least once before anything is checked. It does the checking after to see if the condition is true, as opposed to before. And so this is an example using, this will produce the same thing as the last one. Let's see. Yeah. This will do the same thing as the last while loop. Yeah, this is just a little weird thing to note, is that you need to have a semicolon in the do whiles. Okay, so break is another keyword in C that you can use to help control loops. So for I is equal to 10, as long as I is greater than 0, we'll subtract 1 from I each time we go from the loop. So this printf will print the value of I. And if I is less than 5, then we'll break out of this loop. We don't have to go all the way until I is greater than 0. Or, yeah, as long as I is greater than 0. As soon as I is less than 5, then break tells the compiler, break out of the for loop, and we're done. And it's just a way to help jump out of loops early if you need to, based on some condition. Continue is very similar to break, although it doesn't jump out of the loop. It just skips the rest of the statements within a particular execution of the loop. So in this example, we have we declare and assign the value to I. While I is less than 20, add 1 to I each time you go through the loop, and continue. And what you'll see if you cut and paste this and compile it and run, you'll never see this printf statement, because continue tells the compiler to just go back to the start of the loop and repeat it again and again. It'll keep incrementing I, and eventually it'll break out, but it'll never get to this printf statement. And you can have something like, if something is true, then continue. And that's often a very useful keyword to use to help control loops. Yes, yeah, it works with all the loops, both break and continue. I was asked if that also works with for. Break and continue work with for, while, and do while. Uh-huh.
The condition.
Mm-hmm.
So that's better than
Yeah, so on slide 20, the last bullet is the condition that controls the loop can be modified inside the loop. We have a question about what exactly that means. Look at slide 21. In our while loop, we are modifying the statement because we're increasing the value of counter each time we go through the loop. So counter less than value is changing every time we go through that loop. Uh-huh.
that's the thing.
Yes.
Like,
Yes.
5, right?
Yes. Okay. I'm going to finish up this session, and then I'm going to take a couple minutes break here. So we're going to start in this session and then look at a bit more closely arrays and structures in C. And these are convenient ways of organizing your data, helping you keep track of what data belongs with what other data, etc. So an array, you've already seen actually these strings, we've been calling strings. Those are arrays of characters. It's a multivariable, and it allows you to save a whole bunch of data, or as much data as you want, in a contiguous place in memory. All that data has to be of the same type. You can have an array of any type in C other than a void. And let's see. Yeah, they're declared just like other variables, except you put the size of the array in square brackets at the end. So here we have character, my name, 50 in square brackets. And this means 50 is of size, or my name has 50 characters in it, or can have up to 50 characters. Or my vector has up to, or is composed of 3 integers. And then the last one, my matrix, is a 2 by 2 array. And we'll see a little bit about how that's laid out, actually, in the next session. Is there a limit to array dimensionality? You can run out of memory. You're limited to the size of the memory. I don't know if the compiler itself has a specific limit that it imposes, though. And something like that, it might by default have a limit, and then you might be able to adjust that limit by giving it some option or something like that. Yeah, the last slide is just the references again. And I'll get the next session started, or ready to go, but I'm going to take a break until about 3 at least, maybe 3:05, depending on how people are feeling. But feel free to go through any of those examples and try to run them, try to break them, just mess around with them. That's in the operating system. Yeah, I mean, there definitely is, and it depends on how you have. There's a whole bunch of different ways that you can adjust that. But like, for example, on our systems here, run with more than bytes, the program's going to crash. Let people do that, and that's just because our memory is 32 gigabytes. If you start trying to do more than that, bad things happen. No, yeah, you can call the operating system usually that for any process, whether it's for CPU, the operating system has some address or some size of that it knows about, and keeps track of that. Yeah, it's safest to do that. And get away with just having one immediately after the other, and you don't have that brackets for the outside one. But that's easy to mess up, like you accidentally put a space. Yeah, other than that, it's just messed up. You could put stuff in between, it would just only apply to the outside loop. Right, yeah. Yep. All right, I'm going to start up in another minute with the last session. Unless you guys are not ready yet. It's totally up to you. Okay. Okay, so in the last session we went through our control structures, 3 different types, sequence, which is nothing special to this, it's kind of just what you're used to, and then we looked at if-else, the ternary operator, switch case, and then we looked at the loops and the 3 different types of loops that you can have. Then we started in a little bit with arrays, and this is exactly the slide that I showed, the last slide that you saw. And I got a question before if there's a way to initialize array values more than one at a time. And that's shown here under method 1. So my array is going to be composed of 4 integers. And you can initialize all 4 of them in brackets as shown here. 10, 2, 7, 7, 7, and 4. The content of the array is undetermined until you put a value in it, so it's not really defined. A lot of times you'll get lucky and it'll just be 0, but you can't count on that. You can't be sure. So when you first initialize an array, one of the first things you want to do is assign a value to everything so that you know what's in there. Otherwise, you could definitely run into trouble down the road. And then this is an example of another way to initialize an array. So if you wanted, for example, to just fill my array up with zeros, you could just set up a for loop and set, well, in this case, it's taking keyboard input and assigning whatever you type into the keyboard, that value to this particular element I of the array. But you could also say my array of I equals 0, and then just go through and assign 0 to every value or to every element in the array. Mm-hmm. Again, so in the case of numeric arrays, what you'll have is those first 2 will have some defined value. Or I was asked what if you only assign values to certain elements in the array? Like in the case of character arrays, we would say this character array is of size 50 and only give it maybe a couple of characters. In the case of numeric arrays composed of integers or doubles, it's not going to be defined what any element that you have not assigned, their value is not going to be defined. I believe it's actually the same in the case of the character array. It's just that the functions that are working with that, like the printf, they know how to deal with it, and so you don't have to worry about having extra undefined elements in there. This is kind of what an array looks like. So this is our array from the previous slide. You've got the index for a 4-element array, 0, 1, 2, or 3. And then you actually have the value at that index. So 10, 2, 7, 7, 7, and 4. And so my array of 3 is going to have a value of 4. My array of 1 is going to have a value of 2. And then what do you guys think my array of 2 is going to be? Yeah, 7, 7, 7. Thank you. Something to note that can really trip people up is that the indexing starts at 0. And so that can be confusing at first, but you get used to it after a while. 0 is a number after all, sort of. Um, so yeah, like we said, to access the array elements, you would just type this. This is y array of I, and that'll be the ith element of y array. So you can imagine you can do things like multiplying, doing like a dot operation between vectors, or adding vectors to each other, and going element by element in the vector, but using arrays to do this. So in this example, we have a for loop. Let's say x, y, and z are 3-element vectors, and we can add the array, or the vector y, to the vector z, and then get the vector x after we go through the whole loop. And if you do it again afterwards, it'll just, I will have the value of the last thing that it had, which should be 2. So x array of 2 is equal to y array of 2 plus z array of 2. And this is, a lot of code looks like this, and this is how you set up a lot of linear algebra routines, a lot of basic, the basic libraries that you might be working with, like LOPAC or CBLOS, which you'll see in the future if you get more involved with this. So this is an example of just different ways to, a different way to assign values to the array. Again, you can just do age of 0 equals 23, age of 1 equals 34, and then those will be stored at those locations in the array. And then you can go through and print that out for each one. Again, this is code that you can cut and paste and run it, and this will be the output that you get down here, your output. And you can have arrays of more than one dimension. For example, 2 dimensions, which you could use to represent a matrix. An array of arrays is just called a multi-dimensional array. In this case, we have a 2-dimensional array with 3 rows and 3 columns. And how it's represented in memory is how it's laid out in memory. It's just one big long line within the computer's memory. It just flattens this all out, but it goes along this row, and then it sticks this row at the end of that row, and then it sticks the last row at the end of the next row. But you would access these just like you would, just kind of how you think you would. 0, 0 is going to get you this first element in the matrix, 10, and 1, 2 is going to get you 1, and then 2, 62. So it's row and then column, just like in typical matrix or linear algebra notation. And you can also assign 2D arrays a lot like how you could assign 1D arrays in a single go, using brackets set up like this. So this is an array of arrays. I have my outer brackets. That's the first array. And then that's the outside array. And then the first inside array is this 1, 2. And then the next one is 3, 4. They're calling it sublists and main list in this case. And you can actually do this with even more and more multiple levels of this, but it starts to get really confusing after a while. So in this example, they set up X array, Y array, and Z array and initialize it with these values. And then goes through a nested for loop, just adding X and Y equal to Z. So you can just think of the matrix operation Z is equal to matrix X plus matrix Y. And then it prints out the value of Z array here. And again, this is one that you can just cut and paste and test it out. I was asked if that's the only way to print values is to do loops like this, and in C itself, yes. Now there's libraries to help you do operations like this out there that are totally, pretty much ubiquitous and totally free, that kind of thing, that'll help you manipulate arrays so you don't have to go through some of this every single time. Or you can set up, like, write your own little functions to handle it too. Now we'll move on to structures. And structures are kind of like a way of combining different types of data together. So you could have, in this example, something almost like how a database could be set up. So our structure is type sample, and we'll associate integer A with this type sample and character B. And this is how you would declare it then in the code. Oh, you can use typedef just as kind of a, I don't know, a note-keeping aid or a bookkeeping aid, and just call, instead of saying struct sample every time you want to declare something, in this case it's my sample, you can just say typedef struct sample. That's just going to be a new type. And so for the rest of the code, you can just use the name new type to represent a struct sample type. And it's just to reduce the amount of writing or typing that you have to do. There's nothing deep to it. So here's an example of using a struct and how you get at the members of the struct. Here we have typedef struct point. And there's a double x that belongs to it and a double y. So you can think of it like it's a point in a Cartesian coordinate system. And then we've typedefed it, so now we have a new type named point that we can work with. So the first line in the main function, you can say, oh, type point, my point. And it knows that my point is of this of type struct point that you defined above. And then you get at these members of points just with the dot operator. So my point dot x gets you double x. You can assign that value and use it later on. And same with y. And then you can see in the print statement getting back at those values. And it's just a convenient way to organize your data structures. So I just talked about arrays and structures. And again, they're just ways to organize your data, very convenient ways, and it would be hard to program without them. Now I'll move on to functions, which is a way of organizing your code and being able to reuse functionality in your code without just completely rewriting it. A function is a self-contained block of statements, does a certain task. You've already seen one, main. Main is the first function that we've worked with. You can use it, write it once, and then use it a whole bunch of times, and it helps. It doesn't really make code maintenance easy by any means, but it does help, and it does promote code reusage. Two main steps that are involved: you got to write the function, get a definition, and declare its type, and then you can call the function. We'll see an example of that momentarily. You can say there's two types of functions if you want. They're really just, there's nothing fundamentally different about them. You have standard library functions, which they come with C, like printf or scanf, or you can define your own functions. Yeah, like I just said, these are defined in those header files, like stdio.h. And you just have to include the correct header files to be able to get at these. We talked about scanf a bit already. I think this slide's particularly important. I'll skip over this one. It's just some of the details about how scanf can work. We we've already seen ones like this before where we use scanf to get at the name. This strange looking thing after the percent in the scanf, that'll let you do things like have spaces in the name. It's called, I believe, regular expression. Regular expression, and it's just a way of parsing text. Nothing real deep to it. You just kind of have to look it up and learn how it works. And then just as before, it'll print it out. So how do we write our own functions? That's what's described here. So every function has to have a return type. Void is a valid return type for a function, as is integer, double, even arrays. You can even return arrays. You have to have a name for the function, and then the parentheses afterwards can take arguments to the function. So like the string that you give to printf is the argument to the function printf. You can define variables within the function. These variables will only live within the function. Once you leave, once you exit here, these variables will disappear. You won't have access to them anymore. They're only alive inside these brackets. This function then, as you can see, it just adds two variables that you input from the keyboard and adds them together and prints them out. It doesn't return anything, and that's why it's a void. If it returns something, you'd have to give it a value of whatever it's returning. Here's an example of actually using that function. So we have our header file, as always, stdio.h. And then we have our function add, which we define at the top of the file here. Now, throughout the rest of this source file, we can use add as many times as we like. And so if you can run add to 1, 2, 3, 4 times, it doesn't matter. It'll just run exactly the same code over and over again. Okay, so here's the references again. I don't know. We could go through. There is one more lecture that we could go through, or at least start going through if you guys want to. It's up to you. Bring it up. Yeah, what's in there? Yeah, let's go through this. This is good stuff. If we don't get through it all, that's okay. Just wait a minute. Okay, I'll continue on with the next session. We're going to continue on with our add function example. Sometimes when you're writing a code, you don't want to have to worry exactly where your function definition is. You don't want to have it just directly above your main function. And so you can do a nice thing in C by declaring the function before main, but then actually defining the function somewhere else. And so this is all you have to have for the compiler. If you don't have add declared before the main function, the compiler won't know about it, even if you've defined it later on. But as long as you declare it beforehand, again, declaring is just giving it a name and a type, the compiler is okay. It knows, just like, okay, this guy exists, I'll go look for him somewhere else. Now we'll look at sending input values to functions. First, you have to know the number of values that you want to send to the function, and you also have to know the type to send. So is it an integer or a double, or et cetera, that I want to send to the function? You have to declare those variables first, and you'll use those values in the function. Let's move on. Let's see an example of this. So here we have our add function again, but we can actually just pass the values that we want to add together using the parameters. In this case, we'll call them formal parameters. So add now has two parameters or arguments, int d and int e. And we go down and we look in main. You can see we use the scanf to input those values into our code. And then we can call add with any integer that we want. In this case, we'll just do 1 and 2 for the first example. And then that'll take a copy of 1 and a copy of 2 and assign it to D and assign it to E. And then I can add those together and assign them to C and print that value out. Then we can do the same with the integers that we input from the keyboard, A and B. And so you can add arbitrary integers together using this. Yeah, like it says down here, this note, the actual parameter names, A and B, they don't have to be the same at all as what they're calling the formal parameters. In this case, D and E. In fact, it's usually easier if they're not. Otherwise, it can get kind of confusing. So you can also pass arguments to the function main. So from the command line. You have to change what they call the signature of main. You have to let the compiler know that main wants to accept arguments. And this, as they show on the bottom here, int main with the int argc and character star argv with the brackets, that's very standard. What this does, argc tells you the number of arguments that are going to be passed to main. And argv is the vector of arguments that you're passing to main. I think we'll see what exactly that means in a minute. But this is extremely standard. You can use argc. You can see how many arguments are passed to main, and then you can get at each of these variable arguments later on in your code. See what they have here. Pass value 2.c. Got our include files, stdio.h and standardlib.h. This is going to be the same function add that we had before. They just snipped out the body of the function. And then here we have the new way of defining main so that you can accept arguments. Now you don't have to pass arguments to main, even if you have these parameters defined here. It just gives you the option to now. So in this case, if if our number of arguments is not equal to 3, then we'll throw, we won't do anything. We'll just say, hey, give us the correct number of arguments. Otherwise, we will convert the first argument to an integer and the second argument to an integer, and then add them together. So it's kind of like our previous example of add, where we use scanf, but instead of using some extra function, we're just using the capability of main to take in arguments directly. Yeah, that's a good point. So there's always at least one argument to main. And the first argument is, I believe it's always the program name. So you'll always just kind of skip over that one and then start with the second and the third, etc. That's just how it's set up. Yes, sir, yeah. It's like you do your / executable name, and then in this case you would just give it 2 integers after that, like 1 space 2. Mm-hmm. Yep. Yeah, I was just asked a little bit more detail about how this works. If in this example you were to write on the command line, after compiling // pass value 2, where pass value 2 is your binary or your executable, the first argument would be the first number that you type after pass value 2, and then the second argument would be the second value. So if you could have a 7 and a 9, for example, after that, and then add them together. No, white space is ignored for the purposes of argv. Or actually, I mean, it's not ignored. It indicates that this is a separate argument. And you can have multiple spaces, though. Extra white space is just gobbled up, and don't have to worry about it. Yeah. Okay. So the next slide just goes into the same that I just talked about. argc is the actual argument count. This code wants to have 3 arguments. Main itself has the 2 arguments. Right. So it just explains in a little bit more detail, explicitly, how it works. Okay, so this is another way to use functions, which we haven't quite seen yet. So the return type now, instead of being void, is integer for add. What this means, what we remember for main, is that it has to return an integer value. In this case, it will return the value of C. So this add function is just like our previous one, and the main function is just like the previous example with add. Scanf, scan the values from the keyboard into these integer variables. Pass these integer variables to add, but now add returns an integer. And so we can pass what add returns to the variable C. And it's just a different way of doing it in a often very convenient way. It's kind of clean looking. And this is just the output if you were to compile the last example and run it. Oh, and that's the end. That's what we have at the end of this session for the day. Any questions are very welcome. If people want to work on stuff for the next half hour or so, should be around to be able to help you all out. If anyone online has additional questions, feel free to email me, and we'll do our best helping you out. Thanks. Mm-hmm. The question is, C have objects, and basic C, you can sort of do object-oriented things. Structures are mostly how you would do it, but it's really C++ where you start to get into the serious like object structures and methods and inheritance and all that good stuff. Hopefully we'll have a course on that at some point in the